Hello student, welcome to our lesson 2. Under this lesson we are going to discuss factors affecting electrical energy. Now we have seen that whenever you increase resistance, you increase current, the rise in temperature increases. In other words, the temperature rises or the temperature increases with increase in resistance and time. Therefore, the heat produced by a conductor carrying current depends on the following. 1, the amount of current passing through the conductor. And now here we are saying the heat produced is directly proportional to the square of current through the conductor, provided that the same conductor is used for the same time. So in other words, heat energy is directly proportional to the square of current. So in here we are saying, as you increase the current, the heat energy also increases. Now when you plot a graph of temperature against the square of current, that will be a straight line through the origin. And this shows that the current is or the heat energy is directly proportional to the square of the current. Then from there, the second factor is the resistance of the conductor. Now, heat produced in a conductor, as we have seen earlier, increases with increase in resistance. And that is why in our first experiment, the resistance wire was getting warmer. It was having a higher temperature compared to thick copper wire. We have mentioned that the resistance wire has a higher resistance compared to copper wire. Therefore, from that experiment, we can say that the heat produced in a conductor carrying current is directly proportional to the resistance of the conductor. Again, provided we are using the same current and time. That is, current and time are constant. So, mathematically, we can say that heat energy is directly proportional to the resistance. So again, when you plot a graph of temperature against the length of the conductor or against the resistance, you'll find that it is a straight line through the origin. Then from there, we move to the third factor, and this is time. So we have that time for which current flows through a conductor. So if you keep the current and the resistance constant, and now you increase time, you will find that now the heat energy produced in a conductor is directly proportional to the time. In other words, we are saying, make sure that the current and the resistance is constant. So mathematically, we have that heat energy is directly proportional to the time. And when you plot a graph of temperature against time, again, it will be a straight line through the origin. So in summary, we can say that heat energy, where we are using H, is directly proportional to the square of current, is also directly proportional to the resistance, and also directly proportional to the time. So if we now equate or replace the sign of proportionality with an equal sign and a constant, you will find that our heat energy H is equal to I squared, then multiplied by R, multiplied by T, where I is the current, R is the resistance of the wire, and T is the time taken. So from this summary, we can make a conclusion that the heating effect produced by an electric current I flowing in a conductor of a resistance R in time T is given by H is equals to I squared R T. And this equation is called Joule's law of electrical heating. And this Joule's law of electrical heating, it states that the energy developed in a wire is directly proportional to the square of the current for a given resistance and time, the time for a given resistance and current, and the resistance R of the wire for a given current and time. Remember now, this equation is what we are calling the Joule's law. And this equation is summarizing the factors that are affecting the electrical energy or the heating effect of electrical energy. Then from there, we have something to note. Now we have seen that H is equals to I squared RT. But from Ohm's law, that is current, electricity 2, we know that current is given by voltage divided by the resistance R. Therefore, if we replace I with V over R, that is where we have I, you put V over R, you will find that the equation will be simplified to H is equals to V squared times T divided by R. You can replace and find that one of the R is cancelling out. And that is why you are left with R as our denominator. Then we can move to examples. Number 1, the potential difference across a lamp is 12 volts. How many joules of electrical energy are changed to heat and light when 1, a charge of 5 coulombs passes through it, and number 2, a current of 2 amperes flows through the lamp for 10 seconds. We proceed as follows. Work is charge times voltage. And we know that the energy changed to heat and light is equivalent to the work done. And now the work done will be given by the 5 coulombs multiplied by the voltage, which is 12. So when you multiply, you find that the work done to pass, or if you look at the question, was asking how many joules of electrical energy, and that joules is equivalent to the work done. So in our calculation, you find that it will be 60 joules of energy. Then part 2, you're supposed to get the work done or the joules of electrical energy that is changed to heat and light when we have this kind of current that is passing. Now work done is also given by current times voltage times time. Remember these formulas, we derived them in electric current 2. That is where we discussed about the Ohm's law. So the energy changed to light and heat will be given by 2, that is the current, then multiplied by the voltage, which is 12, and then multiplied by the time, which is 10 seconds. When you multiply, you find that the energy will be 240 joules. Then question number 2. An electric iron box has a resistance of 30 ohms and it takes a current of 10 amperes. Calculate the heat energy in kilojoules developed in 1 minute. We proceed as follows. We start by listing what is given. We have the resistance as 30 ohms, we have current as 10 amperes, and T as 1 minute, which is equivalent to 60 seconds. Therefore, using our formula, H is equals to I squared RT, we just replace the values. You have 10 squared, then multiplied by 30 and multiplied by 60. So when you multiply, you find that you will get 180,000 joules. And because you're supposed to light it in kilojoules, you find that it will be 180 kilojoules. So that is the energy that is being taken by the electric iron box. Then from there, we have another example. An electric cooker has a coil of resistance 5,000 ohms. If it is operated on 250 volts mains supply for 1 hour, how much heat energy does it produce? We proceed as follows. First of all, it is very important to write what is given. We have the resistance as 5,000, we have the voltage as 250, and we have time as 1 hour. So if you convert 1 hour into seconds, you need to multiply 60 by 60, which is 3,600 seconds. Then from there, we now use this formula. Remember, we are given the voltage, we have given the resistance, and we have time. So we can use this formula and substitute our values. And when you do so, you'll find that when you multiply 250 squared times the time, which is 3,600, then divided by the resistance, which is 5,000, you find that the heat energy is 45,000, which is equivalent to 45 kilojoules. Then number 4, we have that when a current of 2 amperes flows in a resistor for 10 minutes, 15 kilojoules of electrical energy is dissipated. Determine the voltage across the resistor. Now in this case, again, we are given all the other parts, but now we are supposed to get our value of R. So first of all, we need to get the voltage. Remember, we are supposed to get the voltage. So using this formula, we have H, that is 15 kilojoules. We have I, which is 2 amperes. And we have time, which is 10 minutes. So we have to convert 10 minutes into second by multiplying by 60. So by so doing, you find that you'll have only one unknown, which is our voltage. So making the voltage the subject of the formula, you need to divide through by 2 times 10 times 60. And when you do that, you'll find that it is 1200. And that is, if you divide 15,000 divided by 1200, you get that it is 12.5 volts. Then from there, we have electric energy and power. Now, the work done in pushing a charge around an electric circuit is given by work is equals to voltage times current times time. That is the work done that is pushing the charge across the resistance wire. But now we know that from here, we can say that work over T, that is you divide through by T here, you'll find that this part you're left with the VI. But we know that power is defined as the rate of doing work. Therefore, work done divided by the time taken is equals to power, because we are saying power is the rate of doing work. So therefore, we can say that electric power is given by P is equals to V times I, as you can see it here, because this part, work over time, is equals to VI, and work over time is power. Therefore, power is equals to voltage times current. But from Ohm's law, we know that V is equals to IR. So, substituting this equation 2 in 1, where we have V, we put IR, you'll find that power will be given by I squared multiplied by R. Remember, now we have replaced V with IR. And that is why now we have having I multiplied by I, then we have R. So power is equals to I squared multiplied by R. Again also, from that Ohm's law, I is equals to V over R. That is if you make I the subject of the formula. So again, instead of now substituting V, we can substitute I in our equation, where we have power is equals to VI. Instead of writing I, you write V over R. And when you do so, you find that the electric power will be given by V squared divided by R. So in summary, we can say that electric power consumed by an electric appliance is given by 1, power is equals to VI, or power is equals to I squared R, or power is equals to V squared divided by the R, which is our resistance. So in other words, you can use any of these equations when you are doing your numerical equations. Now from there, we can be able to get the unit of power. And as you can see here, it is work done over time. We know that the SI unit of work done is joules, and the SI unit of time is seconds. So we can say that the SI unit of power is joules per second. But that joules per second is the same as watt. Therefore, the unit of power is watt or joules per second. Thus, when we have an electric lamp with a power rating of 75 watts, it implies that it is converting 75 joules of electrical energy into heat and light energy in every second. So in other words, we are saying the power is also the same. It can also be defined as the rate of energy conversion. That is 1 kilojoule is equals to 1000 joules. Then from there we have the assignment. Again, the assignment is testing what we have just learned. So make sure that you attempt the assignment with a lot of confidence. Thank you, and let us meet in our next lesson.